Okay, so in terms of the kinetic energy, we can see that this guy here, rho BHL, this is rho times the volume, right? So this is the mass of the tine. Okay, rho times the volume is equal to the mass. And the last thing that I want to say about this is that if you look at these expressions, right, so we've got the elastic strain energy and the kinetic energy, and the thing that we have to do is we have to do these integrals. Right, so we have this one up here, which is the integral of the curvature over the length. This is the integral, actually, oops, I just realized each one is squared, right? So this is the integral of the slope squared. I see there's a missing squared here. Okay, and the last integral is just the integral of the mode shape itself squared. So we got these three integrals. We integrate the mode shape squared, we integrate the first derivative squared, and we integrate the second derivative squared to calculate these things. And so, and this is generic, basically, for any mode shape we can do this. So I'm going to write down what the numerical values are for the particular mode shape that's given in the table. So the integral 0 to 1 of phi1 squared dx bar is equal to 0.397, and the integral of the first derivative phi1 dx squared dx bar is equal to 4.85, and the integral of the second derivative squared squared 0 to 1 is equal to 198.6. Okay, and so what we end up with is that these are the terms that are in, right? So WE is WB plus W sigma, and we could write, in terms of our frequency estimate. So I'm going to write omega 1 squared. This is the frequency of the first mode, is equal to, I've got the elastic strain energy on the top here. Okay, sigma r pH over L times 4.85 divided by mass of the tine times 0.397. Actually, 0.397 times m tine. Okay? And so the way we can think about it is that we have essentially the modal stiffness. Okay, and remember here I've included the residual stress, right? So if there's zero residual stress, this term goes away. And we can think about the thing on the denominator as being the modal mass. So let's call it, since it's the first mode, we'll call this, basically this is K1 and this is M1. And so we end up with our usual expression. We have omega squared is equal to K over M. But these are the modal stiffness and the modal mass. And the last thing that I want to mention is that when we have the point mass included, and that is, right, so what is that point mass? What does it represent? So, because this was, now it's a little ways back. So we're looking at this case. Oopsie. Somewhere I thought I had it actually in here. Oh yeah, here we go. So we're looking at this case where we have a point mass of 1 picogram. I'm going to write this as m point. Okay, 1 picogram acting at the center of the beam. Okay, so that point mass in terms of its kinetic energy, we've got point mass times phi1 evaluated, phi1 squared evaluated at 1/2, right? Because it's evaluated at the midpoint of the beam. And there's no factors of 1/2 here, right? Because when I wrote down the energy calculations, right, the strain energy calculations, oopsie, oh great, these all have the factor of 1/2, and so that drops out in this analysis. And it turns out that the amplitude of the mode also cancels out. So it doesn't matter when we use these mode shapes. They don't have to be normalized mode shapes because they end up in the numerator and in the denominator, and so the amplitude of the mode shape actually drops out. And so what we get for this particular case is using the numerical values given. Actually, here's what I'm going to do. I'm going to put this. So write it as like, this is the modal mass divided by the modal stiffness divided by the modal mass. Here, I'll even write it like this. So I changed my notation a little bit. And so given the numerical values, we get that case 1 gives us F1 is equal to 412 kilohertz, and F2 is equal to 339 kilohertz. Okay, and you have to do a problem like this on the homework. Actually, so I can fit everything. In fact, if I yeah, except that I've lost the modal mass in that. Anyway, F2 is 339 kHz. Oh, sorry. This is case 1, this is case 2. Okay. Now, sometimes when we're using these tuning forks, we actually want to use them as strain sensors. And the idea is that if we change so this right now we're thinking about as a residual stress, but basically any axial stress here will change the modal stiffness. As we increase this axial stress term, modal stiffness is going to go up, and so that's going to change the resonant frequency. So we can use the frequency as a measure of extension. So it says here, like, the double intertuning fork is an excellent sensor for axial stress since it converts the stress into a shift in frequency. And frequency is easily measured, and you can measure it accurately. So you can use a double intertuning fork for a number of different kinds of resonance sensors, so accelerometers, gyroscopes, and we can find an analytical expression for the frequency shift due to axial stress. So the idea is basically stress sensitivity. It's not stress. Sensitivity, we're talking about basically the delta in frequency over the change in stress. So the way we're going to calculate that is d omega 1 d sigma r, okay? And this will actually, I wrote it as, this is going to end up being radians per second per, let's say, Pascal of stress. And I'll write it like this here, so it's delta omega over sigma. So let's say that we want, so we're going to calculate, we'd like to have a large change in frequency for a given input stress change. And so it works out to, so we have that omega 1 is square root k modal over m modal. So d omega 1 d sigma r, actually I'm going to call it d omega d sigma. Okay, d omega d sigma is going to be equal to 1/2 k over m raised to the minus 1/2 times the derivative of that side, the inside part. So it's 1 over m submodal times dkm d sigma. Okay. And so the reason I wrote it this way is if we look back on the previous slide, you can see that the modal stiffness is where, it's right here, sigma is in the modal stiffness. The modal mass does not depend on the stress, right? That should be obvious. The mass doesn't change. Only the stiffness changes. So it's this dk d sigma that we want to evaluate. And it turns out that dk d sigma is going to be bh over L times this integral. Okay, and I'm not going to put in 4.85, I'm actually going to put in this expression. Okay, so, and this guy, well, this is 1 over omega. Okay, 1 over omega 1. So what we end up with is, oops, I need a new slide for this. So we end up with d omega 1 d sigma is equal to 1/2 1 over omega 1 over the modal mass times dk d sigma, which is b h over L times the integral from 0 to 1 of d v1 dx bar squared dx bar. Okay, and for any vibration mode with frequency omega and mode shape phi, we have the sensitivity of that mode to stress is 1/2 1 over omega times 1 over the modal mass times bh over L times the integral from 0 to 1 of, I'm going to write it just like this, phi prime squared dx bar. Stress sensitivity of any mode shape. So different modes will have different stress sensitivities. Okay, different modes will have different stress sensitivities, and this is one of the things I ask on the exam, or sorry, not on the exam, not on the exam. On the homework, I'm going to ask you to calculate the stress sensitivity of different modes of the doublet and tuning fork. Okay, and that's all for this time.